I am so glad you are here in the hush of the evening. You have found your way to Science Blanket, your own soft space for wonder. Have you ever watched the moon move across a slow, dark sky and felt as though you were seeing a long, flowing dream? This evening, we are wrapping ourselves in the mystery of the sun's path. Specifically, the way we chose to divide our world into 24 zones and our hours into 60 small, rolling moments. We usually see a clock as a sharp and busy thing, but it is really just an echo of ancient circles, a series of invisible lines and old, sacred numbers swaying in a soft balance between the turning of the earth and the quiet needs of our souls. From the small, shimmering minutes that feel like smooth silk to the long, heavy shadows of the world's hours that bring a sense of deep peace, the way we measure our lives is the visible sign of a very old and invisible harmony. As we begin, imagine yourself resting in a room of warm, golden sand, feeling as still and as easy as a stone in a stream. You do not need to worry about the math of the sun or the names of the men who built the first trains tonight. Just let the slow, swinging rhythm of the ages wash over you and tuck you in. Allow this blanket of ancient circles and steady, humming time to be your guide as you move toward a deep and mindless rest. Now, take a slow, easy breath. Feel your chest rise and fall, as smooth and as sure as a low ocean wave. Let the heaviness of your day dissolve into the soft, blue shadows of the night. Release your jaw, let your shoulders slide down, and sink into the softness of your bed. Let's explore the quiet wonders of how we share the hours together. In the gentle sweep of history, before clocks ever ticked on walls or chimed from towers, the way we measured hours was something softer, something that changed with the seasons themselves, bending and stretching like shadows across ancient sundials. Early civilizations, those first careful watchers of the sun's arc across the sky, divided their days into hours that were not at all like the hours we know now, hours that grew longer when summer light lingered warm and golden over the land, and shrank shorter when winter brought its cool, early darkness. These seasonal hours, as scholars now call them, flowed with the rhythm of nature itself, expanding and contracting as the earth tilted on its journey around the sun. A summer hour might hold more heartbeats, more breaths, more moments than a winter hour, because it simply followed the longer stretch of daylight that summer offered. This way of measuring felt natural to people who lived close to the land, who planted and harvested by the sun's position, who woke with dawn and rested with dusk. But as centuries rolled forward and astronomers began charting the movements of stars with ever greater precision, this flexible, seasonal approach to hours became something of a challenge, a soft impediment to the hard mathematics they needed for tracking celestial bodies across the vast dome of night. Only when those patient astronomers, those careful cartographers of the cosmos, insisted upon hours of equal length, hours that did not breathe in and out with the seasons but remained steady and unchanging throughout the entire year, did the whole system shift into something more precise, something more mechanical. This move toward 24 equal hours, each one exactly the same duration whether it fell in midsummer or midwinter, transformed how humans could observe the heavens and eventually build those intricate mechanical clocks that would tick away in towers and homes. The equal hour became the foundation for precise celestial observations, allowing astronomers to predict eclipses and planetary movements with accuracy that would have seemed almost magical to earlier generations. The number 24 itself, those 24 equal divisions of a full day and night, carries us back through millennia to the stargazers of ancient Egypt and Greece, those civilizations that looked up at the same moon and stars we see now, seeking patterns and meaning in the wheeling constellations. These ancient astronomers, working without telescopes or computers, only their eyes and their patient record-keeping, decided to divide the daylight into 12 hours and the nighttime into another 12 hours, creating that familiar total of 24 that still governs how we organize our days. There was something elegant in this symmetry, this balanced division of light and darkness into equal portions, even though, as we mentioned, those hours themselves were not equal in length until much later. The number 12 held special significance across many ancient cultures, appearing in the 12 signs of the zodiac, the 12 months that approximate a solar year, and now in the 12 hours that measure half a day. When you double that 12 for both day and night, you arrive at 24, that complete circle of hours that wraps around our lives like an invisible ribbon, organizing our sleeping and waking, our work and rest. But why, you might wonder as you settle deeper into comfort, why does each of those 24 hours contain exactly 60 minutes, and why does each minute divide further into 60 seconds? The answer flows from an even older wellspring of mathematical thinking, from the fertile valleys where the Tigris and Euphrates rivers once nourished ancient Mesopotamian civilizations. The Sumerians, those remarkable people who invented writing and built the first cities, developed what scholars call a sexagesimal number system, meaning it was based on the number 60 rather than the number 10 that forms the foundation of our modern counting. The Babylonians, inheriting this mathematical tradition from the Sumerians who came before them, refined and used this base 60 system extensively in their astronomical calculations, creating detailed records of planetary movements and lunar cycles that would echo through centuries. This is why, when you glance at a clock and watch the minute hand sweep smoothly around the dial, it travels through 60 divisions, not 10 or 100, because the ghost of ancient Sumerian mathematics still governs how we slice our hours into smaller pieces. The Sumerians had a clever physical method for reaching the number 60, one that used the very fingers of their hands as counting tools in a way quite different from how we might count to 10 on our fingers today. They would use the thumb of one hand to touch and count the 3 segments, those small phalanges, on each of the 4 fingers of that same hand, reaching 12 through this tactile counting method. Then, by using the fingers of the other hand to keep track of how many times they had counted to 12, they could multiply 12 by 5, arriving at that significant number 60. This physical, embodied way of counting, using the very structure of human hands as a calculation device, gave them a number system that could be tracked on their bodies, always available, never lost or forgotten. The number 60 that emerged from this finger-counting technique became deeply embedded in their mathematics and astronomy, a foundation that would support centuries of increasingly sophisticated observations of the night sky. When Greek astronomers, centuries after the Sumerians and Babylonians, began synthesizing knowledge from across the ancient world, they encountered this base 60 system and recognized its utility. Hipparchus, one of the most influential astronomers of ancient Greece, wove together the 24-hour day that Mediterranean cultures had established with the Babylonian base 60 system that had proved so useful for precise calculations. Through this marriage of traditions, he defined 1 hour as containing 60 of these smaller units we now call minutes, and each minute as containing 60 even tinier units we know as seconds. The word minute itself comes from the Latin phrase pars minuta prima, meaning first small part, while second derives from pars minuta secunda, the second small part, each one a further division of the hour into increasingly fine measurements. This system gave astronomers the tools they needed to describe positions and movements with the precision their observations demanded, allowing them to specify not just the hour when something occurred, but the exact minute and second within that hour. The number 60 possesses a mathematical beauty that becomes apparent when you consider how many ways it can be divided evenly, how many neat fractions it allows without creating those awkward, messy decimals that go on forever. If you need to split an hour in half, 60 divides cleanly into 30. If you need thirds, you get 20 minutes. Fourths give you 15 minutes, fifths give you 12, sixths give you 10, and you can keep going through many more divisions, each one resulting in a whole number with no remainder, no fractional pieces left over. This divisibility by so many integers, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30, makes the number 60 extraordinarily practical for a measurement system, allowing people to express portions of an hour in simple, intuitive ways. When someone says a quarter hour, we immediately understand 15 minutes. When they say half an hour, we know it means 30 minutes, and these common fractions work smoothly because 60 accommodates them so gracefully. This same mathematical convenience that makes 60 perfect for dividing hours also explains why it persisted through millennia, surviving the fall of empires and the rise of new civilizations, because it simply worked too well to abandon. That Babylonian base 60 legacy extends beyond how we measure time, reaching into how we measure space and angles as well, creating an elegant consistency across different domains of measurement. The circle, that perfect round shape, contains 360 degrees, and this number emerges from the same sexagesimal tradition, 6 times 60, creating a full rotation that can be divided and subdivided using the same comfortable mathematics that governs hours and minutes. This means that when astronomers measure the position of a star in the sky, when navigators calculate their course across the ocean, when engineers design the angle of a bridge support, they are all using a system descended from those ancient Mesopotamian mathematicians who counted on their finger segments thousands of years ago. The degrees, minutes, and seconds of arc that pinpoint celestial coordinates mirror the hours, minutes, and seconds of time that track celestial movements, both systems branches of the same mathematical tree, both rooted in that base 60 soil. This connection between how we measure angles and how we measure time is not coincidental but intentional, designed by ancient astronomers who understood that the sky is a sphere and that tracking objects moving across that sphere requires both spatial coordinates and temporal measurements working in harmony. Hipparchus himself, working on the island of Rhodes in the 2nd century before the Common Era, studied eclipse timings that Babylonian astronomers, often called Chaldeans by Greek writers, had carefully recorded generations earlier. These Chaldean observations, preserved on clay tablets impressed with cuneiform script, contain precise timings of lunar eclipses and planetary positions that stretched back centuries, creating an astronomical database of remarkable depth. Hipparchus recognized the value of this accumulated data, these thousands of observations gathered by patient Babylonian skywatchers who stood night after night recording what they saw, and he used their eclipse timings to refine his own models of how the moon moves through space. The Babylonians had developed increasingly sophisticated mathematical models, including what modern scholars call System B, a complex set of calculations for predicting lunar positions and eclipse timings. Hipparchus took these Babylonian computational methods and combined them with Greek geometry, that distinctive Greek approach to understanding space and form through shapes and proofs, creating predictions that were more accurate than either tradition had achieved alone. This cross-cultural collaboration, though separated by centuries and languages, shows how knowledge flows and accumulates, how each generation of observers stands on the shoulders of those who came before. Ptolemy, writing his monumental Almagest in Alexandria several centuries after Hipparchus, carefully credited his predecessor with this work of validating and improving Babylonian lunar calculations. The Almagest, which would become the standard astronomical textbook for over 1,000 years, explicitly mentions how Hipparchus examined those Chaldean ephemerides, those tables of predicted planetary positions, and confirmed the accuracy of the Babylonian System B lunar periods through comparison with Greek geometric models and newer observations. This attribution, preserved in Ptolemy's text, allows us to trace the lineage of our timekeeping backwards through Greek and Babylonian astronomy, seeing how the 60 minutes in our hours and the 360 degrees in our circles both flow from the same ancient source. When you watch a clock and see the minute hand glide from one number to the next, you are witnessing the visible legacy of Sumerian finger counting, Babylonian astronomy, Greek geometry, and the careful observations of generations of skywatchers who measured time and space using systems so practical, so mathematically elegant, that we still use them thousands of years later, their method surviving in every timepiece, every compass, every astronomical measurement we make today. The ancient Babylonian priests, those careful observers who watched the heavens not merely out of curiosity but as part of their sacred duties, kept records that stretched across generations, records so detailed and so patient that they could perceive patterns invisible to a single human lifetime. Among these remarkable documents, preserved on clay tablets that survived millennia buried in the dry earth of Mesopotamia, sits the Venus tablet of Amisaduqa, named for a king who ruled around 1650 years before the Common Era, a time so distant that it existed before the pyramids had aged into ancient monuments. This tablet, inscribed with careful cuneiform marks pressed into soft clay and then baked hard, contains observations of Venus appearances and disappearances that reveal a 21-year cycle in how this bright wandering star moves through the sky. The priests who maintained these records discovered that Venus, that brilliant evening and morning star, follows patterns that repeat roughly every 21 years, and by tracking these cycles through decades of patient observation, they gained the ability to forecast when Venus would vanish behind the Sun and when it would reappear, when it would move forward through the constellations, and when it would seem to reverse course in that mysterious backward drift we now call retrograde motion. What makes this achievement particularly remarkable is that these priests accomplished this forecasting without any geometric models of planetary orbits, without any understanding that planets move around the Sun in elliptical paths, relying instead purely on pattern recognition, on the accumulated weight of observations that allowed them to say with confidence that what happened 21 years ago would happen again now. This observational astronomy served purposes that extended far beyond simple curiosity about the night sky, reaching deep into the religious and political life of Babylonian civilization through a vast compilation called Enuma Anu Enlil, a collection of celestial omens spread across 70 tablets that connected what happened in the heavens with what might happen on Earth. These tablets, assembled over centuries by successive generations of priest astronomers, correlated specific eclipse timings and planetary configurations with particular omens, creating an intricate system where the movements of celestial bodies could be read as messages or warnings about earthly affairs, about the health of the king, the success of harvests, the outcomes of battles, the stability of the realm. When eclipses occurred, those dramatic moments when the sun or moon darkened in ways that must have seemed almost supernatural to ancient peoples, the priests would perform elaborate rituals called namburbi, incantations, and ceremonies designed to avert whatever disasters the eclipse might portend. These rituals represented a belief that the heavens communicated with humanity and that through proper religious observance, through the correct words and offerings, the negative effects of ominous celestial events could be deflected or softened. The priests did not see themselves merely as passive observers recording data, but as active intermediaries between heaven and earth, responsible for interpreting celestial messages and protecting their society from cosmic threats. The mathematical sophistication that Babylonian astronomers brought to their lunar calculations reveals itself most clearly in their use of that sexagesimal system we mentioned earlier, that base 60 mathematics that allowed them to express complex astronomical periods with remarkable precision. When calculating the length of the lunar month, that period from one new moon to the next, Babylonian astronomers developed a number expressed in their sexagesimal notation as 29 31, 50, 8, 20, which translates in our decimal system to approximately 29.5305994 days. This extraordinarily accurate value, achieved without telescopes or atomic clocks, without any of the technological instruments we take for granted, came from centuries of accumulated observations and the mathematical flexibility of the base 60 system that allowed them to express fractions and perform multiplications with a level of precision that would not be matched in Europe for well over 1,000 years. By multiplying lunar periods by this precise sexagesimal number, Babylonian astronomers could convert between lunar cycles and solar days with accuracy that still impresses modern scholars, predicting when eclipses would occur and where planets would appear with an exactness that served both their astrological purposes and laid groundwork for future scientific astronomy. This same sexagesimal thinking structured how Babylonian astronomers organized the sky itself, dividing the ecliptic, that great circular path the Sun seems to trace through the background stars over the course of a year, into 360 degrees using their beloved base 60 mathematics. They further divided this celestial circle into 12 sections of 30 degrees each, creating what we now recognize as the 12 signs of the zodiac, those familiar constellations like Aries and Taurus and Gemini that the Sun passes through on its annual journey. The choice of 12 divisions reflects not only mathematical convenience, since 60 divides evenly by 12, but also corresponded roughly to the 12 lunar months in a year, creating a satisfying symmetry between the Moon's monthly cycle and the Sun's annual cycle. Within this framework, the priests compiled star catalogues like the MUL.APIN tablets, which listed 60 significant constellations, that number 60 appearing again like a musical theme running through Babylonian astronomy. These 60 constellations were organized along 3 celestial paths named for gods: the path of Ea near the southern horizon, the path of Anu around the celestial equator, and the path of Enlil toward the northern sky, creating a 3-tiered map of the heavens that helped observers orient themselves and track the movements of planets as they wandered through these divine pathways. The MUL.APIN tablets, whose name means plow star in the Akkadian language, represent one of the oldest surviving astronomical compendiums, cataloging those 60 constellations with enough detail that modern scholars can identify most of them with specific star groups we still recognize today. These tablets instructed observers on how to predict when particular planets would rise or set, when certain stars would first become visible in the dawn twilight, using simple instruments like water clocks that measured time by the steady drip of water from one vessel to another, and gnomons, those vertical posts whose shadows track the sun's movement across the sky. The water clock, a technology that seems almost primitive compared to our digital timepieces, nonetheless allowed Babylonian astronomers to measure intervals during the night when the sun provided no shadow to track, letting them time the duration between when one star rose and when another followed, building up through patient observation a detailed understanding of the celestial clockwork. The gnomon, even simpler, just a stick planted vertically in the ground, cast shadows whose length and direction changed throughout the day and throughout the year, providing a solar calendar that marks seasons and solstices, equinoxes, and the optimal times for planting and harvest. Earlier still, from a period stretching from roughly 1800 to 1100 years before the Common Era, Babylonian astronomers created what scholars now call astrolabes, though these ancient instruments differed significantly from the elaborate mechanical astrolabes that would emerge in Islamic and medieval European astronomy. These early Babylonian astrolabes consisted of tablets listing 36 significant stars, 3 for each month of the year, creating a celestial calendar that tied particular stars to particular seasons. What makes these documents particularly fascinating is how they blend astronomical traditions from different regions and cultures that existed within and around Mesopotamia, elements from Elam to the east, from Akkadian traditions in central Mesopotamia, and from Amurru in the west, all woven together into unified sky paths that transcended local traditions. This astronomical synthesis, this gathering together of knowledge from diverse sources into a coherent system, shows how even in ancient times, scientific knowledge flowed across political and cultural boundaries, carried by traders and scribes, by conquered peoples and conquering armies, by anyone who looked up at the same stars and wondered what patterns might be found there. Far to the west of Babylon, in the Greek city of Seleucia along the Tigris River, an astronomer named Seleucus, who lived around 190 years before the Common Era, proposed ideas that would not gain general acceptance for nearly 2,000 years, ideas about how the Earth itself moves rather than sitting motionless at the center of everything. Seleucus championed a heliocentric model of the cosmos, a sun-centered system where the Earth and other planets orbit the Sun rather than everything circling the Earth, building on earlier proposals by Aristarchus of Samos that most ancient astronomers had rejected as counterintuitive and contrary to observation. What makes Seleucus particularly interesting is the evidence he marshaled for Earth's motion, particularly his careful attention to the tides, those daily risings and fallings of the ocean that must have seemed mysterious to ancient peoples. Seleucus observed that tides correlate with the phases of the moon, that the highest tides occur at new and full moon when sun and moon align, and he argued that this lunar connection to tides made more sense if the Earth was rotating daily, if the spinning Earth passed through gravitational influences from the moon that pulled the oceans into bulges. His argument that the Earth's daily spin could be inferred from the regular rhythm of tides, from the daily ebbs and flows that mark coastal life, represents a sophisticated attempt to use earthly phenomena as evidence for cosmic arrangements, though his contemporaries largely remained unconvinced. This same Seleucus made detailed observations of how tides varied with lunar phases, noting that the relationship between the moon's position and the timing of high and low tides suggested some physical connection between the two, some invisible influence that the moon exerted on earthly waters. He wove these tidal observations into his broader heliocentric arguments, suggesting that if the Earth rotates daily beneath the moon's gravitational influence, the patterns of tides would naturally follow the patterns we observe, with two high tides roughly each day as different parts of the Earth's ocean sweep through the regions of lunar attraction. While Seleucus could not explain the mechanism of gravity, a concept that would not be fully articulated until Newton's work in the 17th century, his intuition that celestial bodies influence each other across empty space, that the moon somehow reaches down to pull at the oceans, shows a remarkable physical insight that went against the dominant Aristotelian view that celestial and terrestrial realms operated by entirely different principles with no physical connection between them. Meanwhile, Greek astronomers working in the Mediterranean region continued refining their own approaches to measuring and dividing the heavens, building on foundations that reached back to Babylonian methods while adding distinctively Greek geometrical thinking. Eratosthenes, that remarkable polymath who famously calculated the Earth's circumference by comparing shadow lengths in different cities, approached the problem of dividing circles in a characteristically straightforward Greek manner, using 60 parts simply because it was a convenient and divisible number. But it was Hipparchus, working a century after Eratosthenes, who truly advanced the synthesis of Babylonian computational methods with Greek geometrical models, achieving a level of precision in eclipse timing calculations that sometimes reached accuracy better than 1/10 of a second, an astonishing achievement for naked-eye observations recorded without any mechanical timing devices more precise than water clocks. Hipparchus accomplished this by taking those Babylonian eclipse records we mentioned earlier, those careful timings preserved on clay tablets, and using them to refine the parameters of his geometrical models for how the moon and sun move, creating a system that could both explain past observations and predict future eclipses with unprecedented accuracy. Hipparchus also adopted a Babylonian unit of angular measurement called the cubit, a unit that equaled roughly 2 to 2.5 degrees of arc, using it alongside the sexagesimal division of degrees into minutes and seconds of arc to create a flexible system for expressing celestial positions and measurements. This blending of the cubit, a measurement originally derived from the length of a human forearm and applied to the sky, with the mathematical precision of sexagesimal division, shows how practical and theoretical considerations intertwined in ancient astronomy. The cubit provided a convenient unit for rough measurements and quick calculations, while the sexagesimal subdivision into minutes and seconds allowed refinement to whatever degree of precision the observations warranted. Through this combination of Babylonian numerical methods and Greek geometrical models, Hipparchus created an astronomical system that could describe the positions of stars and planets with extraordinary accuracy, establishing coordinate systems and calculation methods that would persist through Ptolemy's work and into the Islamic astronomical tradition and eventually into early modern European astronomy. His methods and measurements echoing through centuries because they worked so remarkably well, because they represented a synthesis of the best knowledge available from multiple civilizations, all focused on that timeless human desire to understand the patterns traced by lights moving through the darkness above us. In the years before our modern system of time zones brought order to the clock, each individual town and city set its timepieces according to the position of the sun directly overhead, that moment of local solar noon when shadows point precisely north or south and the sun reaches its highest point in that particular location's sky. This meant that neighboring cities separated by even modest distances could show different times on their clocks, differing by several minutes or sometimes more, because the sun reaches its zenith at slightly different moments as you travel east or west across the landscape. What seemed perfectly natural and sensible when most people rarely traveled more than a few miles from home, when the fastest transportation was a horse and carriage and most commerce remained local, became increasingly chaotic as railways began connecting distant cities with regular scheduled service that required coordination across hundreds of miles. Railway timetables turned into bewildering documents filled with multiple time standards, with trains departing one city at a particular hour according to that city's clocks and arriving in another city at a time that made sense only if you knew that the destination's clocks ran minutes ahead or behind, creating confusion for travelers and railway operators alike, making it difficult to coordinate connections and sometimes leading to dangerous situations when trains operating on different time standards shared the same tracks. The Great Western Railway in Britain, one of the pioneering railway companies that helped define how modern rail transport would function, recognized this problem early and adopted Greenwich Mean Time as its operating standard beginning in 1840, bringing all its stations and schedules into alignment with the time kept at the Royal Observatory in Greenwich. They distributed this standardized time using chronometers, those precise mechanical timepieces that could maintain accurate time even when transported, carrying Greenwich time along the railway lines to synchronize station clocks throughout the network. The railway company called this standardized time railway time to distinguish it from the various local solar times that towns still kept for their own civic purposes, and the efficiency and safety benefits proved so compelling that other railways quickly followed suit. By 1855, an astonishing 98% of public clocks throughout Britain had synchronized to Greenwich Mean Time, creating a national time standard driven not by government mandate but by the practical necessities of railway coordination, with the Royal Observatory essentially becoming the timekeeper for an entire nation simply because the railways needed a single reference point that everyone could agree upon. During this transitional period in the 1850s, you could find a curious hybrid reflected in British clocks, mechanical timepieces that accommodated both the old local solar time and the new railway time through an unusual solution. Dual minute hands that swept around the same clock face showing two different times simultaneously. 1 minute hand tracked local solar time, calculated from the actual position of the sun in that particular location sky, maintaining the traditional connection between clock time and celestial reality that had governed human timekeeping for millennia. The other minute hand tracked Greenwich Mean Time, telegraphed from the Royal Observatory using the new electrical technology that allowed signals to travel instantaneously along wires, bringing precise time from Greenwich to distant locations without the delay and drift that affected mechanical chronometers transported by train or ship. These double-handed clocks, which must have seemed quite peculiar to modern eyes accustomed to a single minute hand, represented a society in transition, caught between the ancient logic of solar time that varied by location and the modern necessity of standardized time that ignored the sun's actual position in favor of coordination and efficiency. The refinement of this dual minute hand solution around 1852 reflected improvements in telegraph technology that made it practical to distribute time signals electrically from the Royal Observatory at Greenwich to clocks throughout Britain. Telegraph operators would send precisely timed electrical pulses along the wires at specific moments each day, allowing distant clocks to be checked and adjusted against the Greenwich Standard, creating a network of synchronized timepieces that all agreed on what hour and minute it was regardless of where the sun actually stood in their local skies. This technological capability to transmit time instantaneously across distances transformed timekeeping from an astronomical observation that necessarily varied by location into an agreed-upon convention that could be maintained uniformly across vast areas. The second minute hand on these transitional clocks tracked those telegraphed Greenwich signals, offering people a choice between local solar reality and standardized railway time, though increasingly the latter dominated daily life as railways became central to commerce and travel. Far across the world in New Zealand, that remote island nation at the edge of European colonial expansion, the importance of telegraphic time coordination became so clear that New Zealand became the first country anywhere to formally and explicitly tie its civil time, the time used for all official and civic purposes, to Greenwich Mean Time. In 1868, New Zealand established a standard time set at 11.5 hours ahead of Greenwich, creating a national time zone that applied uniformly across the islands rather than letting each town keep its own local solar time. This decision to peg national time explicitly to the Greenwich meridian came from practical considerations about telegraph coordination, about the need to communicate with British colonial authorities and commercial partners across the world's telegraph network that was rapidly spreading across continents and under oceans, linking distant places into an increasingly synchronized global system. The choice to be 11.5 hours ahead rather than a whole number of hours reflected New Zealand's actual longitudinal position, sitting roughly halfway between 11 and 12 hours away from Greenwich, showing an early willingness to adopt half-hour zones when necessary to match geographical reality. New Zealand's 1868 standard, positioned at 172 degrees and 30 minutes east longitude, corresponding to that 11 hours and 30 minutes ahead of Greenwich Mean Time, prioritized maintaining clear telegraph links with the rest of the British Empire over matching local solar noon perfectly with clock noon. This represented a philosophical shift in how people thought about time, moving from the ancient understanding that noon meant the sun's highest point to a modern understanding that noon meant whatever the agreed-upon standard said it meant, accepting minutes or even hours of discrepancy between sun position and clock reading in exchange for coordination with distant places. New Zealand's pioneering adoption of this Greenwich-based standard time, becoming the first polity anywhere to make such an explicit connection between local civil time and the meridian running through Greenwich Observatory, foreshadowed the global time zone system that would gradually emerge over the following decades as more nations recognized the advantages of international time coordination. Across the Pacific in North America, where vast distances and multiple competing railway companies created even more complex scheduling challenges than Britain faced, an educator and administrator named Charles F. Dowd began working on a comprehensive solution to the time zone problem. In 1869, Dowd devised an initial plan that would divide North America into 4 time zones, each centered on a meridian 15 degrees of longitude apart, with the primary zone centered on 75 degrees west longitude, which runs roughly through Philadelphia. His plan represented sophisticated geographical thinking, recognizing that since the Earth rotates 360 degrees in 24 hours, each hour of time corresponds to 15 degrees of longitude, making 15 degree zones a natural way to organize standardized time. However, when Dowd presented his plan to the railway companies whose cooperation would be essential for implementation, they rejected it, finding it too theoretical and insufficiently adapted to the practical realities of their existing routes and schedules, leaving the problem of multiple conflicting time standards unresolved for more than another decade. Dowd refined his proposal in 1872, creating a version that used natural geographical features like the Appalachian Mountains to draw boundaries between zones rather than following strict meridian lines, attempting to make the system more practical and intuitive by having zone boundaries follow recognizable landmarks. But again, the railroads rejected his plan, finding that his zone boundaries, however logical from a geographical perspective, did not align well with the actual distribution of their stations and route networks, creating complications rather than simplifications for their operations. It would take another decade and a different approach before the railways would accept a time zone system, an approach that prioritized the railroad's operational needs over geographical elegance. Meanwhile, Cleveland Abbey, working within the United States Weather Bureau, recognized that standardizing time would benefit not just railways but also the increasingly sophisticated weather observation and forecasting network that required coordinated measurements from stations scattered across the continent. In 1879, Abbey published a report on standard time that made compelling arguments for synchronizing Weather Bureau stations to a common time standard, showing how weather systems moving across the continent could only be properly tracked and predicted if observations from different locations were accurately time-stamped according to a unified system. His advocacy helped convince Weather Bureau stations to synchronize their clocks, creating a scientific constituency for standard time that complemented the commercial and safety arguments coming from the railways, gradually building momentum toward a comprehensive solution that would serve multiple needs simultaneously. Finally, in 1883, after years of proposals and rejections, the railroad companies implemented a standard time system across the United States, choosing Sunday, November 18th as the day of transition, a day that would come to be remembered as the Day of Two Noons because of how the change was implemented. The railroad's plan, largely developed by William F. Allen, General Secretary of the American Railway Association, divided the continent into 4 time zones but drew boundaries based on the actual distribution of railway stations and junctions rather than following neat meridian lines or natural features, creating a system that served the railway's operational needs first and foremost. On that November Sunday, at precisely noon according to each location's old local solar time, station masters were instructed to stop their clocks if they were in a zone that needed to move backward, keeping them stopped for however many minutes necessary to align with the new standard time for their zone, or to advance their clocks forward if they were in a zone moving ahead. This meant that in some cities, noon arrived, clocks stopped, minutes passed in frozen time, and then clocks resumed showing a new noon arrived under the new system, creating that strange experience of 2 noons in one day that gave the date its nickname. The implementation happened before the International Meridian Conference that would formalize the global time zone system, showing how practical necessity and commercial coordination drove standardization even before international diplomatic agreement established the principles and conventions that would eventually govern timekeeping worldwide. The city of Detroit, sitting near the border between what would become the Central and Eastern time zones, found itself caught in a peculiar temporal uncertainty for more than a decade and a half, cycling through different time standards as the city tried to determine which system best served its residents and its commerce. From 1900 through 1916, Detroit experimented with local solar time, then shifted to Central Time, then moved to Eastern Time, then back again in a confusing succession of changes that made scheduling and coordination challenging for anyone trying to conduct business or arrange meetings with people in the city. The situation reflected deeper tensions about whether Detroit should orient itself economically and temporally toward Chicago to the west, which anchored the Central Time Zone, or toward New York and the eastern seaboard cities that defined Eastern Time. Finally, in 1916, after years of this temporal back and forth, Detroit voters settled the question through a referendum, locking the city into Eastern Standard Time largely because of business pressures from companies and financiers who wanted to operate on the same schedule as New York, where the nation's financial markets opened and closed, where major corporate decisions were made, where the economic rhythms that increasingly governed American commerce originated and spread outward. Across the Atlantic in Geneva, that Swiss city that sits right along the French border, residents in the mid-19th century had to navigate not just 2 but 3 different time systems operating simultaneously in their daily lives, creating a complexity that must have required constant mental translation and adjustment. There was Swiss Standard Time, the official time adopted by Switzerland for national coordination, and there was French Railway Time, used by trains crossing the border and by anyone whose business connected them to the French rail network, and then there was pure local solar time, calculated from the actual position of the sun over Geneva itself, which differed from both of the other standards. People living near the border had to know which time applied in which contexts, checking one clock when catching a train to France, another when conducting official business with Swiss authorities, and perhaps glancing at the sun itself or a solar-adjusted clock when organizing their personal affairs according to the ancient rhythm of daylight and darkness. This juggling of multiple times, this constant translation between different temporal frameworks, shows how the transition from local solar time to standardized zones created periods of confusion and complexity before new conventions solidified and the old ways faded from daily practice. In Germany, even after the nation officially adopted standardized time zones in 1893, many towns, particularly in the southern regions, clung stubbornly to their traditional local solar times for civic purposes, resisting the imposition of a uniform national standard that they saw as serving the convenience of distant authorities rather than local needs. These southern villages developed a practical compromise where they kept public clocks, especially the prominent clocks on churches and town halls that everyone could see, set to local solar time that matched the sun's position in their particular valley or hillside. But when they needed to catch trains that ran on Berlin time, the standardized system that Germany had adopted with its capital city as the reference point, they would mentally add or subtract the necessary minutes, essentially fast-forwarding their perception of time to synchronize with the railway schedule. This created a dual temporal reality where people moved back and forth between local time for daily life and Berlin time for modern transportation, maintaining older traditions even while accommodating new necessities, showing how deeply rooted the connection between local place and local time had become over centuries and how reluctant communities were to surrender that connection even when practical benefits of standardization became clear. Churches across Europe proved particularly resistant to railroad time, viewing the shift from solar time to standardized time as something almost sacrilegious, a human presumption to override the God-given reality of the sun's position with an artificial construct designed for commercial convenience. The Dean of Exeter Cathedral in England became particularly famous for his resistance, actually filing lawsuits against railway companies over their attempts to change public clock times, arguing that the cathedral's ancient responsibility to mark the true hours of day and night according to celestial reality should not be subordinated to the scheduling needs of a modern commercial enterprise. His resistance continued for years until the spread of telegraph technology made time signal enforcement increasingly practical and the weight of public convenience increasingly overwhelming. Eventually, even the most tradition-bound ecclesiastical authorities yielded to telegraph-enforced standardization, recognizing that maintaining their own separate time system isolated them from the rhythms of daily life that their congregations actually lived. But their resistance speaks to how profound a change standardized time represented, how it altered humanity's relationship with the cosmos and with the ancient practice of reading time from the sky. Decades before the International Meridian Conference and before Sandford Fleming's proposals captured widespread attention, an Italian mathematician named Chirico Filippanti proposed what may have been the first genuine worldwide time zone system in a book he published in 1858 with the whimsical title Miranda, which translates roughly as wonderful things. Filippanti's system envisioned dividing the entire globe into 24 time zones, each 1 hour apart, though rather than centering the prime meridian on Greenwich as would eventually become standard, he centered his first zone on Rome's meridian, proposing that his home country should serve as the temporal reference point for the world. His proposal, written in Italian and published in a book that mixed mathematics, astronomy, philosophy, and political commentary, never achieved the widespread attention or political momentum that Fleming's later proposals would generate, perhaps because Italy lacked the global imperial reach that Britain possessed, or perhaps simply because the timing was not yet right, the need not yet urgent enough, the telegraph and railway networks not yet extensive enough to make global time coordination seem necessary rather than merely interesting. Filippanti's 1858 book Miranda outlined what he called longitudinal days, 24 temporal zones arranged around the globe based on meridians of longitude, each zone maintaining an hour's difference from its neighbors, creating a system remarkably similar to what would eventually be adopted internationally decades later. He even proposed a universal time for astronomical observations, recognizing that scientists needed a single time reference for comparing observations made at different locations around the world, anticipating the development of what we now call coordinated universal time. Filippanti's work predated Fleming's famous proposals by more than 2 decades, yet his ideas never gained traction outside a small circle of Italian intellectuals. His book never translated into English or French, where it might have influenced the broader conversations about time standardization that would intensify as railways and telegraphs continued spreading across continents and under oceans. History sometimes credits Fleming alone with inventing the time zone concept, but Filippanti's earlier work reminds us that good ideas often emerge multiple times independently, and that who gets remembered for an innovation often depends as much on timing, language, political power, and communication networks as on the actual originality or quality of the idea itself. Sir Sandford Fleming, a Scottish-born Canadian engineer whose name would eventually become synonymous with time zone standardization, emerged as the most effective advocate for a worldwide system of 24 standard time zones during the late 19th century. Not because he was necessarily the first to propose such a system, but because he had the connections, the persistence, the communication skills, and the political savvy to turn a theoretical proposal into practical international policy. Fleming occupied a position within the British Empire's engineering and transportation infrastructure that gave him credibility with both government officials and railway executives. the two groups whose cooperation would be essential for implementing any time standardization scheme. His advocacy extended over years, even decades, involving countless letters, reports, presentations, and conference appearances, gradually building momentum for the idea that the world should adopt a rational, comprehensive approach to time rather than continuing with the chaotic patchwork of local times and competing standards that made international coordination increasingly difficult. Fleming's personal investment in time standardization grew from a frustrating experience he had in 1876 when he missed a train in Ireland because of a confusing timetable that mixed up morning and evening times, showing either post-meridium when it meant ante-meridium or vice versa, leaving Fleming stranded at a station for hours waiting for a train that had actually departed much earlier than he realized. This annoying personal inconvenience, the kind of travel mishap that anyone who has navigated complex transportation systems can sympathize with, crystallized for Fleming the broader chaos that resulted from having no clear, universal system for expressing time unambiguously. He began thinking about how civilian timekeeping might benefit from adopting something similar to the astronomical day used by scientists, which counts a full 24 hours from midnight to midnight without the confusion of duplicate morning and afternoon hours, and from there his thinking expanded to encompass a complete reimagining of how humanity might organize time globally, leading eventually to his proposals for worldwide time zones, all referenced to a single prime meridian. Fleming's credentials as an engineer included his work surveying routes for the Canadian Pacific Railway through Yellowhead Pass, one of the more challenging sections where the railway had to cross the Rocky Mountains, that formidable barrier of peaks and valleys that separated Canada's western coast from its central plains. The survey work he conducted in 1872 took him through harsh mountain terrain, facing bitter cold, difficult logistics, and the constant challenge of finding practical routes through geography that seemed almost hostile to railway construction. This direct experience with the difficulties of building transcontinental transportation infrastructure, this intimate familiarity with how railways needed to coordinate across vast distances and through multiple regions, gave Fleming a practical understanding of why time standardization mattered. Why it was not merely an abstract intellectual puzzle but a genuine operational necessity for the transportation networks that were beginning to tie continents together. Beyond his work on the Canadian Pacific Railway, Fleming had surveyed over 3,000 miles for the Intercolonial Railway, that line designed to connect the maritime provinces of eastern Canada with the more populated regions further west, providing him with years of hands-on experience in the practicalities of railway construction and operation. This extensive surveying work, measuring distances, calculating gradients, determining optimal routes through varied terrain, honed both his technical skills and his understanding of how railways functioned as systems requiring coordination across hundreds or thousands of miles. These skills and this understanding fueled his global time standardization campaign, giving him concrete examples and practical arguments to complement the more abstract theoretical case for worldwide zones. When Fleming spoke about time coordination, he spoke not as an abstract theorist but as someone who had personally grappled with the challenges of making railways work across vast distances, someone who understood viscerally why synchronized time mattered for safety, efficiency, and coordination, lending his advocacy a grounded practicality that helped convince skeptics and move the conversation from whether time zones were a good idea to how exactly they should be implemented and administered. Across the globe. Fleming's vision for reforming time began with something that might seem simple but actually represented a significant departure from centuries of habit. He proposed adopting a 24-hour clock face instead of the traditional 12-hour dial that required distinguishing between morning and evening hours using those easily confused designations ante-meridium and post-meridium. The traditional system, where the hours counted from 1 to 12 twice each day, created inherent ambiguities that had caused Fleming's own mistrain in Ireland and countless other scheduling errors wherever people needed to coordinate activities across distance or communicate times in writing where context might not make clear whether 7 meant morning or evening. A 24-hour clock would eliminate this confusion entirely, counting straight through from midnight to midnight, from 0 to 23, or from 1 to 24 depending on the convention chosen, making every moment of the day uniquely identified by a single number that could never be mistaken for any other time. This proposal faced resistance from people accustomed to 12-hour clocks, people who found something natural and intuitive about the way traditional clocks divided day and night into 2 equal 12-hour segments. But Fleming argued that clarity and precision should outweigh the comfort of familiar habits, especially as the world grew more interconnected and coordination more essential. Fleming's initial proposals went even further than simple time zones, envisioning what he called cosmic time, a universal 24-hour clock that would apply uniformly across the entire globe, providing a single temporal reference point unlinked to any particular meridian or location on Earth's surface. Under this system, everyone everywhere would use the same clock time, though that time would correspond to different positions of the sun in the sky depending on where you stood on the planet. Someone in London might eat lunch when cosmic time showed 1300 hours and the sun stood high overhead, while someone in New York eating lunch at the same cosmic time would see the sun still climbing toward its midday peak, and someone in Tokyo would be eating lunch under stars with the sun far below the opposite horizon. Fleming imagined this universal time freeing humanity from the tyranny of local solar time, creating a single worldwide reference that would make international coordination effortless. However, this radical proposal proved too divorced from people's lived experience of day and night, too counterintuitive for general adoption. So Fleming refined his thinking toward a compromise system of 24 time zones labeled with letters from A through Y, skipping the letter J presumably to avoid confusion with the letter I, each zone representing a distinct hour offset from a prime meridian, allowing local time to roughly correspond with solar position while still providing clear coordination across distance. Fleming even commissioned a custom pocket watch around 1880 that embodied his dual-time concept, with one side of the watch showing traditional local time and the reverse side showing his proposed cosmic time using those alphabetical zone designations A through Y. This watch, a physical manifestation of his vision, allowed Fleming to demonstrate how his system might work in practice, flipping the watch from one side to the other to translate between local solar time and universal coordinated time. The watch served as both a conversation piece and a practical tool during his advocacy efforts, letting him show skeptics and supporters alike how his proposed system could coexist with traditional timekeeping, how someone could maintain connection to local solar rhythms while also participating in a globally synchronized temporal network. The watch represented Fleming's recognition that any successful time reform would need to accommodate both local and universal needs, providing people with access to both types of time depending on their immediate purposes. The mathematical elegance of Fleming's scheme came from dividing the Earth's 360-degree circumference into 24 zones, each one exactly 15 degrees of longitude wide, creating a perfect correspondence where moving one zone eastward would shift local time forward by exactly 1 hour, while moving one zone westward would shift time backward by 1 hour. This neat mathematical relationship made the system easy to understand and calculate, allowing anyone who knew which zone they were in and which zone they were communicating with to quickly determine the time difference between locations. The 15-degree width of each zone represented a compromise between the ideal of many narrow zones that would closely match local solar time everywhere and the practical need for zones wide enough that large cities and their surrounding regions could share the same time without too much divergence between clock time and solar time. Within any 15-degree zone, clock noon might differ from solar noon by up to 30 minutes, since the zone boundaries themselves fell halfway between the hour meridians, but this seemed an acceptable trade-off for the benefits of having large regions sharing synchronized time. Although Fleming suggested those letter names for the zones, running from A through Y with J omitted, countries implementing time zone systems largely chose to ignore this alphabetical naming scheme in favor of numeric offsets expressed as positive or negative hours from Greenwich Mean Time. Saying we are at +3 hours or -5 hours proved more intuitive for most people than memorizing which letter corresponded to which zone, and the numeric system easily accommodated the half-hour and even quarter-hour zones that some countries adopted to better match their geography or political boundaries. The alphabetical scheme, while elegant in its own way, seemed to add an unnecessary layer of abstraction, requiring people to translate between letters and hours when the hour offsets themselves conveyed the information more directly. However, Fleming's lettered zones did not disappear entirely from history, as one letter in particular achieved lasting significance in specialized contexts. Zulu time, that term familiar to pilots, sailors, and military personnel worldwide, represents perhaps the most enduring legacy of Fleming's alphabetical zone naming scheme, with the letter Z designating Greenwich Mean Time itself, now more properly called Coordinated Universal Time or UTC. In aviation and military communications, where precise time coordination across vast distances is essential and potentially life-saving, Zulu time provides that universal reference point that Fleming originally envisioned, that single clock time understood identically by everyone regardless of their location. When air traffic controllers coordinate flights crossing multiple time zones, when military operations require synchronized actions across continents, when ships navigate the seas using astronomical observations, they reference Zulu time, that direct descendant of Fleming's vision for a universal temporal standard. The persistence of this single letter from Fleming's original scheme, even as the rest of the alphabet faded from use, shows how certain aspects of good ideas survive even when the complete system gets modified or replaced, how practical needs preserve useful elements while discarding those parts that proved less essential. Fleming invested his own money and considerable time in 1879 preparing detailed papers for presentation to the Canadian Institute, papers that analyzed shipping schedules and railway timetables, demonstrating through concrete data the chaos and inefficiency created by the lack of time standardization. His research meticulously documented cases where ships arriving in port encountered confusion about timing, where railway connections failed because of incompatible time standards, where business communications suffered from ambiguity about when things would happen or had happened. Fleming used this data to make a comparative argument for choosing Greenwich as the prime meridian for the global system rather than alternatives like Rome, which Philippanti had suggested, or Washington, which some American advocates preferred for reasons of national pride. Greenwich, Fleming argued, already served as the reference point for the majority of the world's shipping, with most nautical charts and navigational tables calculating positions based on Greenwich longitude, making it the pragmatic choice even if other meridians might have theoretical or political advantages. This self-funded research showed Fleming's deep personal commitment to the cause, his willingness to invest his own resources in gathering the evidence needed to make a convincing case to skeptics. When Fleming presented his refined 24-zone proposal to the Royal Canadian Institute in 1879, he encountered significant skepticism from audience members who found his ideas too radical, too disruptive of established practices, or simply unnecessary given that existing systems, however chaotic, had somehow managed to function well enough for current needs. Some questioned whether ordinary people could adapt to thinking in terms of time zones rather than solar time, whether the public would accept clock noon occurring when the sun was not yet overhead or had already passed its peak. Others worried about the political implications of choosing any particular meridian as the prime reference, recognizing that this choice would confer a kind of temporal primacy on whatever nation happened to host that meridian. The skepticism Fleming faced delayed initial support for his proposals, forcing him to continue his advocacy campaign, to present more data, to address objections, to build coalitions of supporters among scientists, engineers, railway executives, and government officials who could help transform his vision from an interesting idea into practical policy. The slow process of building consensus, of overcoming institutional inertia and human resistance to change, tested Fleming's patience and persistence, but he continued advocating for his cause year after year, recognizing that fundamental reforms rarely happen quickly. Beyond his work on time standardization, Fleming held strong engineering opinions that sometimes proved controversial, particularly his advocacy for building railway bridges from iron and stone rather than the cheaper and more quickly constructed wooden bridges that many railway companies preferred. Fleming argued that wooden bridges, while initially less expensive, posed serious fire risks and required more frequent maintenance and eventual replacement, making them less economical over the full lifespan of a railway line. His stance drew criticism from those who prioritized minimizing upfront construction costs or who questioned whether the fire risk was truly as serious as Fleming claimed. Vindication for Fleming's position came through tragic experience as wooden railway bridges burned with alarming frequency, sometimes from locomotive sparks, sometimes from deliberate arson, sometimes from wildfires spreading through the countryside, causing service disruptions, expensive emergency replacements, and occasionally injuries or deaths when trains encountered burned bridges with insufficient warning. Fleming's willingness to take controversial stances based on his engineering judgment, even when those stances cost more in the short term, reflected a philosophical approach that valued long-term safety and reliability over immediate economy, the same kind of forward-thinking perspective that allowed him to see past the familiar chaos of local times toward a future of coordinated global zones. The International Meridian Conference convened in Washington, D.C., in October of 1884, bringing together delegates from 25 nations to address the question of standardizing the world's prime meridian and laying groundwork for international time coordination. This conference, though it had no binding authority to force nations to adopt its recommendations, represented a crucial diplomatic moment when the world's governments formally considered and largely endorsed the principles that Fleming and others had been advocating for years. The delegates voted to establish a single prime meridian running through the Royal Observatory at Greenwich, chosen both because British maritime power meant Greenwich already served as the reference for most of the world's navigation and because choosing an existing widely used meridian seemed more practical than designating some arbitrary line that would require everyone to change their systems. The conference also endorsed the principle of dividing the world into 24 time zones, each 1 hour apart, though the specific boundaries of those zones would be left to individual nations to determine based on their geography and political considerations. This conference transformed time standardization from a collection of private proposals and isolated national adoptions into an internationally recognized system with diplomatic backing, creating momentum that would gradually bring most of the world's nations into alignment with Greenwich-based time zones over the following decades. Though full global adoption would take many years and some nations would resist or delay implementation for various political, cultural, or practical reasons. The delegates who gathered in Washington for the 1884 International Meridian Conference, representatives from somewhere between 25 and 27 countries depending on how you count territories versus independent nations, reached a fundamental agreement that would reshape how humanity relates to time across the globe. They agreed that all local times, wherever people might live or work or travel, should be referenced to Greenwich Mean Time as the universal baseline, the 0 point from which all time zone offsets would be calculated. This meant that every region adopting standard time would define its clocks not by local solar observations, but by how many hours ahead of or behind Greenwich it sat, creating a web of temporal relationships all anchored to that single meridian running through the Royal Observatory on the Thames. The agreement represented a remarkable achievement of international cooperation, a moment when national delegations set aside competing interests and regional pride to embrace a common standard that would benefit global commerce, communication, and coordination, even though implementing this agreement would require years of additional work and face continued resistance in various quarters. France and Brazil, however, stood apart from this consensus, abstaining from the vote to adopt Greenwich as the prime meridian, their abstentions reflecting both national pride and genuine concerns about surrendering temporal sovereignty to a foreign capital. France particularly balked at accepting British dominance in yet another domain, already chafing under Britain's naval supremacy and colonial reach, reluctant to have French clocks essentially bow to Greenwich's authority. The French maintained their own Paris Mean Time as a national standard and held out against switching to Greenwich Base Time until 1911, nearly 3 decades after the conference, stubbornly calculating their official time as Paris Mean Time retarded by 9 minutes 21 seconds. A formula that technically avoided saying their time was based on Greenwich while functionally achieving the same coordination by expressing French time as an offset from the British standard. This compromise of pride allowed France to eventually join the global system while maintaining the linguistic fiction that Paris, not Greenwich, remained their temporal reference point, showing how deeply questions of time intertwined with questions of national identity and international prestige. During the conference debates, some delegates proposed establishing a neutral meridian that would avoid cutting through major continents, perhaps running through the Pacific Ocean where it would inconvenience the fewest people and offend no major powers by running through their territory. This proposal had a certain diplomatic elegance, avoiding the appearance of favoring Britain by choosing Greenwich, but practical considerations overwhelmed this theoretical neutrality. 21 countries voted against the neutral meridian proposal, recognizing that Greenwich already served as the working reference for most of the world's maritime navigation and that choosing an arbitrary ocean meridian would require massive changes to existing charts, tables, and instruments without providing clear benefits beyond avoiding hurt feelings. The vote demonstrated that pragmatism trumped symbolism, that the world's nations preferred adopting an existing widely used standard rather than creating a new one from scratch, even if that meant acknowledging British temporal primacy. The rejected neutral meridian proposal faded into history as a curious footnote, a road not taken in the development of global time coordination. By the 1920s, roughly 4 decades after the Washington Conference, standard time zones based on the Greenwich Meridian had achieved nearly worldwide adoption for civil, commercial, and railway purposes, transforming how hundreds of millions of people organized their daily lives. The system that had seemed radical and unnecessary to many skeptics in the 1880s had become so thoroughly normalized that new generations grew up never knowing the old chaos of local solar times, accepting as natural and inevitable that their clocks showed the same time as cities hundreds of miles away while differing by precise hour intervals from cities thousands of miles distant. Railways ran on coordinated schedules that passengers could consult with confidence. Businesses could schedule telegraphic communications and later telephone calls knowing that both parties understood what 3 o'clock meant. International shipping operated with clear timetables that eliminated confusion about arrival and departure times. The success of time zone standardization illustrated how quickly human societies can adapt to new systems when those systems solve genuine problems and when institutional support makes adoption the path of least resistance. Despite the theoretical elegance of 24 neat 1-hour zones dividing the globe like orange segments, each exactly 15 degrees of longitude wide, Actual implementation diverged significantly from this geometric ideal as countries bent their time zone boundaries to serve political, economic, and geographic priorities that had nothing to do with astronomical theory. National borders rarely follow meridians, and forcing a country to split into multiple time zones simply because it happened to span more than 15 degrees of longitude often created more problems than it solved, particularly for smaller nations where having multiple time zones seemed absurdly bureaucratic. Geographic features like mountain ranges or rivers that formed natural regional boundaries often made more sense as zone dividers than arbitrary meridian lines. Economic relationships between cities mattered more than longitudinal position, with regions preferring to share time with their major trading partners even if pure geometry suggested they should be in different zones. The result was a complex patchwork where zone boundaries zigzagged across maps following political borders, regional identities, and practical convenience rather than the clean theoretical lines that appeared in Fleming's original proposals. Some places departed even further from the ideal by adopting half-hour or even 45-minute offsets from Greenwich rather than whole-hour differences, creating time zones like UTC plus 5 hours and 30 minutes or UTC plus 5 hours and 45 minutes that cannot be explained by simple division of the Earth's circumference into 24 equal parts. These fractional zones demonstrated that political choice and local preference could override the pure mathematical grid, that nations and regions felt empowered to set their clocks wherever they believed best served their interests rather than feeling bound by international convention to pick from 24 predetermined options. The half-hour and quarter-hour zones complicated international coordination somewhat, requiring more careful attention when scheduling across these boundaries, but the countries using them judged that disadvantage acceptable compared to the alternatives of either splitting their nation into multiple whole-hour zones or accepting clock times that diverged too far from local solar noon. China provides perhaps the most dramatic example of political considerations overriding geographical logic in time zone adoption, spanning roughly 60 degrees of longitude from its eastern coast to its western borders, a distance that theoretically encompasses 5 full-hour zones in the standard 15 degrees per hour system. Yet China maintains a single nationwide time zone at UTC plus 8 hours, meaning that when sunrise occurs in the eastern cities, western regions remain in deep darkness for hours, and when western regions enjoy afternoon sun, eastern areas already experience evening twilight. The Chinese government prioritizes national unity and administrative simplicity over matching clock time with solar time, judging that the symbolism and practical convenience of everyone in the vast nation sharing the same time outweighs the awkwardness of sun positions that sometimes align poorly with clock readings. This choice reflects how time zones serve political and social functions beyond mere coordination, how decisions about clocks can express and reinforce ideas about national identity and centralized authority. India similarly resisted the Greenwich system for decades after the 1884 conference, maintaining Bombay time, which ran UTC plus 4 hours and 51 minutes, as its standard for half a century following the international agreement. The British colonial authorities eventually imposed Greenwich-based Indian Standard Time at UTC plus 5 hours and 30 minutes in 1906, but even then, India chose a half-hour offset rather than a whole hour, positioning itself precisely between two standard zones to minimize the maximum divergence between clock time and solar time across the subcontinent's width. This choice reflected both practical geography and a desire to maintain distinctive Indian identity within the global time system, asserting that India would adopt coordination with Greenwich but on Indian terms, with Indian timing, in an Indian way that served Indian needs rather than simply accepting whatever whole-hour zone Britain might have preferred for administrative convenience. The world map of time zones reveals numerous other examples where local or political considerations created deviations from the neat 24-zone ideal that Fleming had envisioned. Newfoundland maintains UTC-3 hours and 30 minutes, refusing to simply join the Atlantic time zone that surrounds it, asserting through its distinctive half-hour offset a separate identity from mainland Canada. Nepal sits at UTC plus 5 hours and 45 minutes, that unusual quarter-hour offset distinguishing it from Indian time to the south and Chinese time to the north, a temporal declaration of independence from larger neighbours. The tiny Australian settlement of Eucla uses UTC plus 8 hours and 45 minutes, serving a handful of people in a remote location with its own unique time. Lord Howe Island maintains UTC plus 10 hours and 30 minutes, while Kiribati stretches all the way to UTC plus 14 hours, the furthest ahead of Greenwich that any inhabited place goes, and the Marquesas Islands sit at UTC minus 9 hours and 30 minutes. Each of these unusual offsets tells a story about local identity, about political choices, about the ways that time zone decisions reflect and create community boundaries, about how the seemingly simple question of what time it is becomes entangled with deeper questions of who we are and with whom we wish to synchronize our lives. Samoa provides an extraordinary example of how time zones intersect with economic priorities and international relationships through its decision in 2011 to jump forward across the international date line, that imaginary line running roughly along the 180th meridian where one calendar day becomes the next. Samoa skipped Friday, December 30th, 2011 entirely, going straight from Thursday the 29th to Saturday the 31st, losing a full day from its history because being west of the dateline had become economically disadvantageous as Samoa's primary trading relationships shifted from the United States toward Australia and New Zealand. When Samoa was aligned with American time zones, sharing Thursday when Australia already experienced Friday, Samoan businesses found themselves constantly a day behind their major trading partners, unable to conduct same-day business, always waiting for partners to catch up or racing to catch partners who were ahead. By jumping across the date line to the western side, Samoa repositioned itself temporally to share the same calendar day as Australia and New Zealand, even though this meant reversing an earlier decision from 1892 when Samoa had jumped the other direction to align with America, showing how time zone and date line choices remain fluid, subject to reconsideration as economic relationships evolve and priorities shift. How even something as seemingly fixed as what day it is can change. Through collective decision when communities judge that change serves their interests. The decades following the Second World War witnessed aviation's explosive growth from a specialized military and commercial venture into a mass transportation system that connected continents and carried millions of passengers annually across vast distances at speeds that would have seemed almost magical to earlier generations. This aviation expansion accelerated the push toward uniform hour-wide time zones across the globe, as airlines operating international routes needed clear, consistent temporal frameworks for scheduling flights, coordinating crews, managing fuel stops, and ensuring that passengers could understand when their planes would depart and arrive. The complexity of air travel, where a single journey might cross multiple time zones in a matter of hours, made fractional offsets and irregular zone boundaries increasingly problematic, creating pressure on regions that had maintained half-hour or quarter-hour differences to conform to the simpler whole-hour standard that aviation authorities preferred. While some places resisted this pressure and maintained their distinctive offsets as expressions of local identity, many regions that had used half-hour zones for decades gradually shifted to align with neighboring whole-hour zones, judging that the benefits of simplified air travel coordination outweighed the satisfaction of maintaining temporal distinctiveness. The post-war aviation boom thus became another force, like railways in the 19th century, pushing humanity toward greater temporal standardization, though this time the pressure operated globally rather than just within individual nations or regions. Russia, that vast nation stretching across 11 time zones at its widest extent, more zones than any other country, has struggled repeatedly with the question of how many distinct time zones it actually needs or wants to maintain. In 2010, the Russian government decided to merge its 11 zones down to just 9, consolidating some regions into shared time zones in an effort to promote national unity and simplify administration across the enormous country. The logic suggested that having fewer time zones would make coordination easier between distant regions, would strengthen the sense of a unified Russian nation rather than a collection of temporally fragmented territories, and would reduce confusion for citizens trying to communicate or conduct business across the country's vast expanse. However, this merger generated significant complaints from regions forced to adopt times that diverged substantially from their local solar noon, creating situations where morning darkness or evening light felt misaligned with daily rhythms, where children walked to school in darkness or workers commuted home in harsh afternoon sun when their bodies expected twilight. By 2014, just 4 years after the consolidation, Russia reversed course and restored some of the eliminated offsets, bringing the number of zones back up in response to these regional complaints, demonstrating how difficult it remains to balance the administrative convenience of fewer zones against the human preference for clock times that roughly correspond with the sun's position, showing that even in the 21st century, even with all our technology and global connectivity, the ancient connection between solar position and experience time continues to shape how people want their clocks to behave. Space stations orbiting high above the Earth, like the International Space Station that circles the planet roughly every 90 minutes, encounter a temporal situation entirely unprecedented in human history, where the spacecraft passes through sunrise and sunset 16 times in each 24-hour period as it races around the globe at speeds approaching 18,000 miles per hour. For astronauts aboard these stations, the traditional connection between time and the sun's position becomes completely meaningless, as they experience neither stable day and night nor even the consistent daily rhythm that someone on Earth's surface experiences regardless of their latitude. The solution that space agencies have adopted involves using coordinated universal time, that modern descendant of Greenwich Mean Time, often abbreviated UTC, as the temporal standard for space station operations, creating a 24-hour cycle that has nothing to do with solar passes visible through the station's windows and everything to do with maintaining coordination with mission control centers on the ground and providing astronauts with some stable temporal framework around which to organize sleeping, eating, working, and exercising. This represents perhaps the ultimate decoupling of human time from solar time, a situation where clock time serves purely organizational and coordinative functions with no pretense of tracking natural celestial cycles, foreshadowing how humanity might organize time if we eventually establish permanent settlements on other planets where day lengths differ radically from Earth's 24 hours, or on generation ships traveling between stars where the sun becomes just one bright point among many, in an unchanging stellar backdrop. The practical benefits that drove time zone adoption in the first place, those advantages that convinced skeptical railway executives and government officials to embrace what initially seemed like unnecessary complexity, manifested most clearly in how standard time zones drastically simplified railway and telegraph scheduling across regions that had previously operated on incompatible local times. Before standardization, creating a railway timetable required accounting for dozens or even hundreds of different local times along a route, with each station keeping its own time based on local solar noon, forcing schedulers to calculate not just travel times between stations but also the time differences between each pair of stations, creating tables so complex that errors became almost inevitable. Telegraph operators coordinating messages between distant cities faced similar challenges, needing to translate between multiple time standards to accurately timestamp when messages were sent and received, sometimes failing to account for all the conversions and creating confusion about the sequence of events. Standard time zones eliminated this chaos by ensuring that all stations within a zone shared the same time, reducing the complexity of scheduling calculations enormously and making timetables comprehensible to ordinary travelers who could now simply read the departure and arrival times without needing to understand anything about longitudinal differences or solar calculations. Perhaps most importantly, standardization reduced accidents and dangerous situations that arose when trains operating on incompatible time standards shared tracks, when miscommunication about timing led to trains departing when they should have waited or arriving unexpectedly at junctions where other trains had not yet cleared. When the fundamental confusion about what time it was created the possibility of catastrophic collisions that killed passengers and crew. The safety improvements alone, even setting aside the convenience and efficiency benefits, justified the disruption of abandoning local solar time for standardized zones, making time zone adoption not merely a nice improvement but a genuine life-saving transformation of how railways could operate safely across continental distances.